Hello, this is Max. We're working on Fall 2012, Midterm 2, Problem 3b. We're looking at the max path function. It takes an instance of the tree class from Study Guide 2. Tree class is right over here. It is meant to return the maximal sum of internal entry values on a path from the root to a leaf of a tree. So this is going to see what's the biggest sum we can get from going from the root to a leaf. Okay, let's look at our tree class first before we dive into the problem. Looks like it's different than the tree class that we've learned in lecture in spring of 2015. This is more like a binary tree, right? We've got a self.entry and then we've got a left and a right tree. And we don't have any assert statements, but we're just going to trust that this left and a right tree are going to be actual trees or the value none. So you can assume that your tree is well built, assuming that the doc tests. So okay, this doc test has a well built tree, so we're good. So let's first draw out what this is going to look like, see if it makes sense. So we've got a tree that has an entry 3 and then a 4, tree negative 2, it's got an 8 and a 3, okay? What's the maximal path here? Well, it looks like so this is 7, the maximal path here this is 1, 9 if we take this branch, and then 6 minus 2, 4 if we take this branch. So 9 looks like the best thing. Okay, good, that works. So max path for tree 9, none. Let's draw another tree, 9, then we've got none. We've got a tree that has 1, and then negative 2, 5, 2, none. Okay. Now what's the maximum path here? 9, 1, 10, negative 2, 8. It's going to be 8, some here, and then either go 10 or we can go 13. And 13 looks like the highest, and so we're going to get 13. Perfect. Okay, so now let's actually look at the implementation that we have here. We start with paths equal to a list that has the item 0 in it. Now if tree.right is not none, so if we have a tree.right, we're going to figure out what the max path of tree.right is, which is the highest, what's the best sum that we can get from tree.right. Then we're going to append it to our paths list. And then if tree.left is not none, we're going to do paths.append max path tree.left. So we're going to pick and then we do tree.entry equals max paths. Okay, so what we're doing here is we're picking the best path from either our left tree or our right tree. Our left tree or our right tree are going to return the highest valued path that we can get from either the left tree or the right tree. And then we're just going to trust the recursion. This is going to return the best path. And then the only thing we have to do from there is we have to do tree.entry plus equals max paths. Okay, cool. So this looks like it's going to work. Let's run through these two examples. But first, let's read the question. So true, false to indicate which of the following statements about max paths is true. True, false, it returns the correct result for all doc tests shown. Okay, so this is something we can just run through. So we start with that paths that's equal to 0. Leave room in that list. This is when we're looking at this whole tree. Okay, cool. So if tree.right is not none, in this case it's not none, right? We're going to call max paths on this tree right here. So we'll make a new paths directory that's going to be 0. And then we'll call this again. Tree.right is not none. Then we're going to append max path tree.right. In this case it's 3. And so tree.right is called tree.right. Tree.right is just a single entry 3. So tree.right is not none. This is false. Tree.left is not none. This is false. Tree.entry plus equals max paths. Max paths is 0. So we're just going to get 3. So now we have up here paths.append. We can just append 3. We'll do the same thing over here, 8. And now here we want to do tree.entry plus equals max paths. So we're actually going to change, looks like we're actually going to change tree.entry because we're considering this tree right here now. So we're actually changing tree.entry to be 8 plus, we had negative 2, negative 6, right? Because 8 is the max of 0, 3, and 8. Okay. Oh, not negative 6, I'm sorry. Just regular 6. Just 6. Okay. So now we're done here. We're going to return this up. So now we can add a 6 to this 3 here, or this list for this great tree here. And now we can take a look at our left branch. Tree.left is not none. We consider 4. We're just going to add 4 to our list. And now we add the max of our paths to our tree.entry. So we're going to get this is going to be 9. Now our tree is different, but we've correctly returned 9, so this doc test passed. Okay, let's try this here. We're considering this big tree at the beginning. Starts with a paths that's going to be 0. Okay, so now what do we do? So now we want to consider tree.right is not none. Tree.right is not none, it's this tree here. Okay, so here we're going to start with a new, and try and keep track of our paths lists. Our paths list here, now we've recalled it here, we start with 0. Tree.right is not none. Oh, tree.right is none here, so we're not going to do this. Tree.left is not none. Yeah, that's true. So now we're going to call max paths on this. Start with another list that starts with 0. Now here we have 5 and 2. We can just see from inspection that these are going to be leaves, and so we can just put them on our list. Now we're modifying tree.entry to be the sum of the max. So this is going to turn into 3, right? So our max is 5. We do -2 plus 5 is 3. Great, we're done here. We can return up here, up to our big tree here, and so we've not added none, but we have added 3 to our list. And now we're modifying tree.entry equal to the max of these paths. Tree.entry plus equals 3. This is going to be 4. Now this tree is done. We've returned the best path we could get from here. Going to go up here, add 4 to our list. We're done here. We return the max of our paths. This is going to be 9 plus 4 is 13. It's going to change to 13. All right, check. Yeah, that's awesome. Okay, sweet. So this looks like it's returning correct result for all doc tests shown. Now the next question, it returns the correct result for all valid trees with integer entries. So integer is anything that's sort of a whole number from -infinity to infinity, and we're using max. Okay, so it's tempting to just sort of look at these and be like, well, we've included negative numbers in our input here, and it looks like we've been pretty good about our inputs. So maybe it's just true, but this is actually really hard. This is like something that that I stared at for a long time. So you've got to make sure you resist the temptation just to be like, okay, it returns the correct result for all valid trees with integer entries. So this is like, whenever you see something that's all valid trees, you should sort of raise an eyebrow, because there are lots of potential possibilities. So you should think about testing all your possibilities. So let's test some pretty basic cases, right? So the basic cases we can test positive. We pass in some positive number, right? With no children. So if I just pass in a positive number with just 2, then the max path that I could return is going to be paths is equal to 0. And then if tree.right is none, I don't have a tree.right, I don't have a tree.left. Tree.entry plus equals max paths. My max paths is just 0, so I'm going to return 2. That looks like that works. What if I pass in a -2? Okay, so paths is equal to 0. If tree.right is not none, fine. Paths.append, max paths. This doesn't happen, this doesn't happen. Tree.entry plus equals max paths, -2. Okay, that works as well. Now let's try a single child. We'll just try a single right child. We'll try a positive and a negative. Well, let's try positive first. We've tried positives up here actually, so maybe we can just try a negative. Okay, so negative. So this should return 0, right? As our best path that we can take, because we have to go from our leaf to a root, and we need to include all entries. So path starts at 0, and now we do tree.right is not none, that's true. Max paths.append, max path tree.right. You see this is just a leaf, so we can just add it. And now we get to the problem. Tree.entry plus equals max paths. Max paths here is just 0, and so we're going to get 2 plus 0 is equal to 2. And that's not what we want. We expected 0 out as a result. So 2 plus 0 is 2, and we were expecting to do 2 plus -2 should be 0. Okay, we can see that this doesn't work because we've included a max entry. We're taking the max of paths, but if all of our paths are negative, then we're just going to return a 0. So this is not what we want. Okay, great. So we can see that this doesn't work for if we just have all negative entries as our leaves. So that's good to know. So we can see that. It may change, mutate its argument value. yeah, so we pass in tree, and we can see that as we went through this, we changed tree, right? So clearly this is going to actually change the argument value. It may run forever on a valid tree. Well, a valid tree is going to end with none as its default values for self.left and self.right. A valid tree doesn't have any loops, right? And it's not going to... What else do we know about valid trees? Okay, yeah, so in this particular tree doesn't have any parent pointers, and left and right are also trees. So that's a valid tree. And so since we're going down to our base case of checking whether or not something is none for each of them, I feel pretty safe saying that this is just going to not run it forever on a valid tree. It looks like we've done our base cases pretty well here. Tree.right is not none, tree.left is not none. And then we're just doing something. We're not doing a ton of like crazy recursion with left and rights. It's gonna not work on a valid tree. This is something that requires a little bit of intuition and thinking about it for a while. So yeah, okay. Feel free to ask questions on this one. This one is a little tricky. Okay, so let's look at the second thing. So this is an order of growth problem. Define a simple mathematical function f of n such that evaluating max path tree on a tree with n entries performs theta f of n function calls. Theta f of n function calls. So function calls, max path, tree.right, max path, tree.left. For each of our nodes, we're only at most calling a function twice. So we have one function call here and another function call here. And max, so we have another function call here. So it looks like for each of our entries, we're doing 3 function calls. Depending on whether or not you consider plus equals a function call, you can, maybe 3, maybe 4. And we're visiting each of our nodes only once, right? So we go here, we check here, and then we look at each of our children. And we're only ever visiting each of these nodes once. And since we're only ever visiting each of these nodes once, we're going to do a total of 3n computations, right? If we're passed in a tree with n nodes. So we can say that f of n, we can just say it's going to be n, right? Theta f of n means, theta n means we're going to do sort of linear, the number of function calls we make is going to grow linearly with the number of nodes that we pass in for our tree. So this is something that's a little tricky. This also takes a little bit of intuition. What I would do is I would sort of look and see how many function calls I make in each of my recursive calls, and how many recursive calls am I going to make for a tree. And I'm going to make one for each of its nodes, right? So, okay, yeah. Anyway, if you have questions about this, feel free to ask on Piazza or ask on YouTube, and we'll get them answered. Thanks for watching.